Hello boys and girls. So I think a half a year ago or so I made a video where I discussed in fairly broad generality the derivative properties of the softmax. This is like, a relation that with sigmoids is used a lot in neural network theorems. And relatedly here we talk about LogSumExp, which is very closely related to the softmax. And I explain how it indeed relates to the maximum function. What is the difference? I've seen some derivations online just recently. That's why I think of it, which were fairly confused. I think if you actually take a step back and look at what holds in generality, you can learn something, and that's why we do this here. So the context in which I discuss the first lemma is the following. We have some space X and we have some sort of norm functions, right? You can think of it as the norm. You can think of it as the absolute value on the reals. We're not going to use all the properties. We just need this homogeneity for having nice formulas. And we have any symmetric B, some function of two arguments where you can swap the arguments. And firstly, what holds is this relation that we have here, B of the maximum of x and y minus x on the one hand, and maximum of x and y, the same value, minus y, equals b of just 0 and then the absolute value of the difference. We will in a second abstract away from the maximum even. To define a maximum, we need some non-strictly ordered space at least. But yeah, this is the setup that we're going to actually use. Now let's just prove this thing for the maximum at least. Firstly, a norm property is that it swallows up a minus sign. We have by assumption that this B is symmetric. So this is without loss of generality completely symmetric in x and y. And then if x is bigger than y, bigger equal than y without loss of generality, what we have here is x minus x, which is 0. And then what we have here is the maximum of the two minus the smaller one, which is x minus y as well. And, by this property, this is just the absolute value here. Okay, so this is fairly clear to see, I would say. And this fact that we can always swap around the arguments, it was placed a major role in the derivation of relating the LogSumExp to the maximum function below. Here, just for the sake of it, we can abstract away even more from this theorem here. So if we have any, I call this here flag function. So you have any property or, in this case, let's say a fixed proposition P, and this flag function which just decides on them based on this, with classically speaking, there are basically two worlds. Either this f denotes x or this f denotes y. This is our generalization of the maximum function. Then if there is a group operation between these elements, then we have this equality here. You can think about it for a second. It's just, playing around with the inverses in a group. And this is just a straight generalization of what we saw here. I mean, you can use, I write it down in this set kind of way. You can also use like some symmetric function and take these elements as arguments, and then you have this. And further, if we are in a set module, then we can write this ugly expression as so. And if we are as above in this partial order, then we can choose the maximum function, and then we get back to what we just had. In this case, I used norm notation for this absolute value here. So this must be an absolute value in the sense that it should not map to another space. It should not map from a vector space down to the scalar values, but yeah, you get the drift. And also by considering a different property, like not greater equal but smaller equal, you get the same relation also for the minus, for the minimum, and there's just a minus there. Okay, so go to applications. The first two are going to be very trivial. You might have seen them before. So I'm going to treat this max and min at the same time. I just write m, which depends on x and y, for both, and the case where it's a maximum is the plus case, and I do the minus case basically all at once. So let's consider different symmetric functions B. The first function you will think of is the addition of two numbers, let's say. Then the left-hand side of this equation becomes 2m minus x minus y, and the right-hand side is the addition of null plus something, so it's this norm. And then you can solve for m, and then you get this nice relation, which is quite important, I think, to keep in mind or to remember. You know that the maximum is this mean of the sum and the difference, because I think for if people think of non-differential continuous functions, they might think of the absolute value function, and they see this function with the 90-degree angle in it, and they grok, okay, it doesn't have a unique derivative at the origin, and this is like a nice example. Whereas the maximum function, at least in my mind, feels more abstract and feels more discrete, doing a case distinction. But as this result show that you also know, at least on the number line, these are basically the same functions. They're like there's an affine function that relates them, and so you should think when you see some common strange formula and there's a maximum function there, it might help to replace just the absolute value function there, and then it doesn't look as scary anymore, because absolute value functions pop up everywhere. If you, for example, look at the gravitational field, where you say, the vector divided by its norm, or any propagator in physics of the form e to the minus, and then this distance between 2 points, you can also think of this as the maximum function. Okay, this is just a side note. The second most simple symmetric function might be the multiplication. You plug that in, then the equation becomes this second degree polynomial equation, and then you solve it, and basically the same thing comes out again. The absolute value is just written here in terms of square root of the square. And now the last relevant case, if B is the SumExp with a minus sign here. So a SumExp I define here to a base B. You fix a base B. In the numerical example that I will show you in a second, B is 5, but of course the standard thing is to use the e from the exponential function. You have here this sum of exponents. You take any vector that has n components. You take this finite number of elements. You plug them all into the exponent for some fixed base and sum them up. And we choose this thing, just two elements, vector with just two elements, and we have a minus sign for to get to the final formula that we want. And here I remind you of a bunch of other properties that this has. Of course, we have the convention that b to the power of 0 is just a 1, and if we have like an offset with the 1 vector, then we can pull this out because it's just exponential functions. We also have LogSumExp to the base b defined as such. And yeah, and then I'll show you again this formula if you have forgotten it already. So here in this formula you have the same m here and here, right? Max minus x, max minus y, you might think of it. So we can use this calculation rule here with pulling out the constant. We get this kind of thing. It's divided because there's a minus sign. We can bring this over, and then suddenly we have a formula that relates the SumExp with the maximum and the this absolute value norm function, right? And then you can take the logarithm and use the logarithm rules, and then you say explicitly how these two functions differ. So the LogSumExp is indeed extremely close to x, and the more so if this x and y are further apart, because if x and y are further apart, this absolute value is more bigger, and then e to the minus this value goes against 0. The log of 1 is 1, and so you see how you have here this nicely, this function on the left hand side is poorly continuous in all the entries, whereas here is basically the sum of two non-differential functions, non-smooth functions, where the smoothnesses are the same, they cancel out here, so to speak. And that's why this is like a good replacement, a drop-in for the max that you might want to use if you want to have your, for example, neural network differentiable so that you can do gradient descent and don't have to worry about the different possible derivatives at certain points. Yeah, and here finally I do like a numerical example in Python. There's a little bit of a problem here that I use, Python has to the power of as star, and the way I have implemented my wiki, star becomes just bold syntax highlighting, as in many markdown things. So here it has num is b to the power of x plus b to the power of y, and it interprets this wrongly. But okay, for this reason I've put the numbers here. So you have, for example, if you take base 5 and x is 1.2 and y is 3.4, just some random numbers, then the left-hand side, the SumExp of base b equals 5 of these two values becomes some relatively large number, so 244. And then you can also compute this thing, and you can use this formula to compute the max actually in terms of these continuous functions. And as you see, I do this here. The maximum of this x and y is of course this bigger value, 3.4, and it comes out up to numerical error exactly correctly, and similarly for the minimum. I hope this this clarifies the relation between first max and the absolute value as two continuous functions, and why, if you combine them correctly, because they're actually affinely linearly related, you can basically easily get rid of the non-differential point and use just move points with this neat trick. And I hope you saw that the main formula that is like the sort of confusing thing, that the fact that you can swap around these arguments and have like sets which by case distinction are actually the same, even if it might take you a second to see it, right? So where do I have it? Like this this formula here. Maybe this is not super like intuitive. I mean, it is clear if you think for a second about it, but if you see it the first time, you could not bet your life that it's right. But maybe this explanation helped to see this sort of general framework in which this holds, which is very similar to like a number line with some Banach structure on it. Okay. Good night.